So this one becomes, Ampere's law becomes curl of V minus mu naught epsilon naught dE by dt equals to mu naught into J free, the free current density, plus the bound current density, plus the polarization current density. Now, if we replace the relationship of these free currents, the bound current and the polarization current in terms of the magnetization and the polarization here, we would have, well, first for this one, when you replace the bound charge density, which is related by that, we would have the divergence of E equals to rho free plus rho bound now becomes minus the divergence of the polarization P over epsilon. And this divergence of epsilon naught E equals to rho free minus divergence of the polarization. So if you bring this one in here, you would have the divergence of epsilon naught E plus the polarization P is equals to rho free. What did we call this? The displacement vector. So this would give you the divergence of the displacement vector D equals to rho free. On the other hand, for the Ampere's law, the curl of B minus the mu naught epsilon naught, or let's use this time, dE by dt. You know, last time when we come up with this equation, when we modify Ampere's law, we say that this term is related to what? It's related to the displacement current. The reason why it's not included in here, it is the displacement current, if you remember, that's the current that exists in a parallel plate capacitor, right? You remember? So in that plate, there is no charge, right? It's just a simple change in electric field is the one that would cause this current. So it's not really actual movement of charge. When we talk about current, in general, it's just the movement of a charge, right? So bound current is the movement of electrons about their spin or around the orbit, and the free current is the movement of the free electrons. At room temperature, if the material is a conductor, these electrons are not bound to the nucleus, so they are free to move around inside the material. So that's the actual displacement inside the material of the electron. So that's also involves current. And polarization current, that is just the actual movement still while they are bound to the nucleus, but a small displacement from their equilibrium position is the one that generates the polarization current. So all these three involve a real charge. But this one, even if it is we call it a displacement current, it doesn't really involve charge. It's a result of the electric field. So that's why we put it in this term instead of on this side. All right, so this becomes mu naught J free plus J bound, which is going to be curl of M and JP, that's going to be plus a time derivative of the polarization P with respect to T. So this would, if you divide both terms by mu naught, you would have the curl of B over mu naught minus epsilon naught dE by dt equals to J free plus the curl of M plus dP by dt. All right. So now, just like here, where we left only the free stuff, the free charge density, just leave only here on the free current. So that's, if you break this one on this side, you will have curl of B over mu naught minus the magnetization M and minus of d by dt of epsilon naught times the electric field plus the polarization P.
Minus the polarization.
Yeah, I took out the minus from both terms. Yeah.
I watch it.
Yeah. So that's going to be equals to J free. So we know that this is the displacement vector, and this one is the auxiliary field. So that's going to be curl of H minus dD by dt equals to J free. So these are the two equations that would change when you deal with Maxwell's equation inside R. All right, so let's see some an example that illustrates, about the bound current, the free current, the displacement current. Okay, here it says, a seawater at frequency, linear frequency equals 4 times 10 raised to 8 hertz, has permittivity epsilon, which is 81 times the permittivity, electrical permittivity of free space, and the magnetic permeability, which is about the same as the magnetic permeability of free space. And it has a resistivity, which is the inverse of conductivity of that much. So the first part of the question is to find the free, that's the conduction electron, the conduction current, and the polarization current, and the bound current densities. So in the second part, we want to find the ratio of the amplitude of the conduction current to the displacement current. So as a hint, it gives you to consider a parallel plate capacitor immersed in a seawater. So